So let's start to interpret this so that we can get, let's say, interpretation of kinetic energy again. So the first thing that we should say here, kinetic energy is energy and therefore stored work. It's meaningless to talk about kinetic energy by itself. Only changes in kinetic energy are meaningful. I've said this again and again and again. And it doesn't matter what kind of energy we look at this thing. So now, if I look at it from the work energy theorem, it says that if I have external work, I can change the kinetic energy of a system. So then, the way I like to think about this picture-wise, it says that K1 is equal K1 plus the external work gives me now the change in kinetic energy. So in this picture that we have, we imagine that we have something like this. I have this amount of initial kinetic energy, which has no meaning. Then there's a certain amount of external work that is done. So the only thing that's meaningful is not K1 or K2, but only how I transfer this work to changing the kinetic energy. Only this guy is meaningful. Once again, this is meaningful. Anything else is not meaningful. That's what we mean by the work energy theorem. So again, we have discussed this in other issues here. So let's keep going on here. So now what we're going to say here is that work can increase, decrease, or not change kinetic energy. So that means here is that if I have a speeding up car, then that tells me that I have an increase in kinetic energy, which then implies that the work that was done is positive, which then tells us that the change in kinetic energy will be positive. If I have a slowing car, then that energy is a decrease in kinetic energy. And therefore, that tells me that the external work is negative. So then I'm going to have a negative change in kinetic energy. And if we have a constant speed, then that means that I have zero change in kinetic energy, which then typically means here is that I have two compensating works. That means there's a work that's going to increase the kinetic energy, and then there's going to be work that decreases the kinetic energy. And we then say that these guys are going to do what? They're going to offset each other. And as a consequence, then the change in kinetic energy is zero. So that's the things that we want to be looking at here. So now let's get into the details. 3. Kinetic energy depends on speed and mass separately. So now let's look at what we mean by this dependence here. So in this situation, let's talk about velocity dependence. I'm going to say, let's look at the velocity dependence on kinetic energy. So remember, the wording is important here. So how do I want to look at this? Well, let's say that we have a car that's now speeding up again, very similar to as before. And so what we're gonna think about this physically here is that physically it is harder to make a car go faster. That means that I'm going to have a larger work, but that's exactly the same as a larger change in kinetic energy. Now, it's going to be easier to make a car go slower. So therefore, that's going to take a smaller work, and therefore, by definition, I'm going to have a lower change in kinetic energy. So picture-wise, how do I draw this? Okay, so let's look at a couple of pictures here. So the first picture that I imagine is that I see this here. I have a car. Okay. So if I stick to the same process as before, I imagine that this car is only moving at some speed v1. So when I'm looking at this car here, what I'm seeing here is that I expect that if I'm going to have a slower change in speed here, then I imagine that I still have my sucker pushing on this thing. Maybe I should think about the sucker still. And so I imagine that I'm applying a force that's external to the car, and that's the cause of why there's external work here. So again, this is my system, and this is the car, and you could see that that's external work. So now what I want to do here is that I want to take the exact same scenario here. And I want to move them, let's say some distance, something like this here. But this time what I'm going to do here is that I'm going to say is that because this person has continued to push, the speed has gotten higher. And the reason why it got higher here is that we see that there's this amount of displacement right in this picture right here. Now, what I want to do here is that I want to move this back here because I'm going to try to utilize more space here. So once again, I have a displacement where the force and the displacement are in the same direction. So what do I see here? Well, if I think about my work here, I could imagine that this car starts off with this amount of kinetic energy. And then I can redraw this a couple of ways, and you should pick to see what works best for you. And then I'm going to have this amount of external work that's done. And then afterwards, these two can also be written where they're standing right on top of each other. Now, the reason why I like them standing on top of each other is because we know that afterwards, we end up with a higher kinetic energy. So when I'm looking at these guys, the only thing that's meaningful, which I think the first picture does not show you very well, but the only thing that's meaningful is this guy right there. This is what we call meaningful. So that's the picture that I have right here. So now what I want to do here is that we said that was a car that I get moving at a slower speed, requires a smaller amount of work, and therefore it has a lower kinetic energy. But what if I have this situation again? Okay. Now what we imagine here is that we have the same picture again. But now there's a difference. What's different? We have to push harder to make a car go faster. So in this situation, I'm going to say that this has a bigger force acting on it. So if it's a bigger force acting on it, then there's got to be more work for the same distance. So then picture-wise, I imagine my picture now looks something like this. I have this amount of kinetic energy that I started with. But what I do know is that now I'm doing more work. And because I'm doing more work, what's going to happen? Well, if I stack them right on top of each other, like this, then what's going to happen here is that I'm going to have a larger kinetic energy, which I'm going to call K prime. So in this case, I'm going to say that this speed, because we're applying a bigger force, should have a higher speed afterwards. So now, what do I know? I only know that when I do work, I change the kinetic energy. How much do I change the kinetic energy? By this amount. And again, that is meaningful. Everything else is meaningless, but that picture with the delta K. So if you say, so some people will say, hey, this car, the second car, has higher kinetic energy. That's meaningless. To say that the second car has more kinetic energy is meaningless. It has a larger change in kinetic energy, and therefore required more work to change its motion. So picture-wise, we then say this here. So then if I use the work energy theorem, it goes something like this. So then in the language of the work energy theorem language, we then say the following thing. In the first car, we applied an external force, but this external force was small compared to the second car. In the second car, we had a larger external work because we had a larger external force doing work on the car. So instead of calling it work, we now say, well, that's a smaller change in kinetic energy. This guy had a higher change. So the language then says larger work is the same as a higher change in kinetic energy. If I have smaller work, that's the same as saying that this is a lower change in kinetic energy. And the reason why the change in kinetic energy is different here is because each of these cars have the same mass, but its final speed was larger for the second car from its initial speed. So then we come in here and we just say this had a higher speed, this guy had a lower speed. That's what the speed dependence is. Now I can play the exact same game Again,